Beneath the cold geometry of Orion, a single ember breathes Betelgeuse, the red giant that dimmed before the world's eyes, and then returned, leaving questions brighter than the star itself. Tonight follow a calm, unbroken trail from shimmering skin to hidden furnace where dust can mimic disaster, rhythms, whisper of deep structure, and a final message may arrive as neutrinos before any light. Expect a spectacle without danger, a map of echoes and winds, and a promise kept by patience. When the countdown truly begins, we will know first and see everything that follows. Betelgeuse, the red beacon on Orion's shoulder, fades by nearly 2/3 in late 2019 and early 2020, a naked-eye change that startles skywatchers and unsettles modelers of dying giants. The consequence is immediate. If a familiar star can stagger this dramatically, then the clock toward its ending must be read with new care, because false alarms and real warnings may look deceptively alike. This narrative promises to reveal what signs would rise first if Betelgeuse truly enters its prelude to a supernova, and how those signs differ from the theatrical but survivable tricks of dust and surface storms. To begin, the winter sky becomes a stage. A red coal dims against hard blue cold, and the outline of the hunter seems to breathe. Evidence appears in careful measurements as well as unaided eyes, but the eye alone is enough to feel the stakes. A star that bright dimming so quickly suggests either a veil was thrown across its face or something inside sagged. The first payoff arrives here. A dramatic change in brightness can come from nearby dust, rather than a failing core, a distinction that keeps alarm from turning to fear. Dust is simple to grasp. Tiny grains condense in cooling gas, and a cloud crossing the line of sight acts like a curtain. But there is a catch. Only certain patterns of change fit that curtain, while others hint at deeper shifts. The scene sharpens as instruments around Earth and in space point toward Orion. Interferometry, a technique that links telescopes to see fine detail, sketches a mottled disk as if continents of light drift across a star. The so what is direct. The surface is not smooth, but sculpted by huge convective cells, each a continent-sized upwelling of hot gas. Such cells can briefly lower brightness, where they rise and cool, and they also help loft material that becomes dust. A visual anchor hangs in the mind, a slow-turning sphere the colour of embers, its face patched by moving islands of brightness. Next comes the second payoff, when a star like Betelgeuse coughs out a plume, and that plume cools into dust. Just off the surface, the dust can temporarily block part of the star and create a steep drop in light, then slowly clear as radiation, and winds disperse it. But the intrigue deepens because timing matters. Historic records from careful observers, later joined by the American Association of Variable Star Observers, show Betelgeuse has bright and dim seasons, a semi-regular rhythm like long ocean swells crossing and beating. These rhythms, known as pulsations, are simple at heart. The outer layers breathe in and out. When the breaths overlap or shift, the light curve wobbles. The consequence here is a baseline. The star's normal gives a ruler against which anomalies can be tested. Yet the great dimming stretches far below any familiar trough, and that anomaly refuses to sit comfortably within older cycles. The next image is more intimate. Think of a lattice of light trembling as waves cross inside a Red Sea. Sometimes peaks amplify, sometimes troughs cancel, and the whole face seems to quiver. But there is a deeper question behind the surface. What does the interior say? The interior is a layered furnace with shells, where different elements fuse like nested matryoshka dolls, and at the very heart an iron core not yet formed but fated to appear. A new concept enters and is kept. Small shock breakout is the first flash when a buried shock reaches the surface. That moment lies in the future, but its absence during the dimming is itself instructive. The payoff builds absence of a flash, absence of a surge in high-energy light, and calm neutrino detectors all argue that the dimming was not collapse. The star therefore remains alive in its turbulent normal, and the stakes shift from imminent catastrophe to careful watchfulness. The winter sky offers another anchor. Orion rising over dark hills, Betelgeuse now recovering to a steady glow, while nearby Rigel holds icy blue. The mind asks what could make the next episode look different. The answer begins with multi-wavelength eyes. The Hubble Space Telescope, the James Webb Space Telescope, and large eyes on the ground, such as the Very Large Telescope, can see warm dust and hot gas. Separately can map molecules that form when plumes cool, and can take the temperature of knots on the stellar face. The So What Titan's dust has a spectral fingerprint, and so do hot patches, and combining these fingerprints with the timing of pulsations yields a test for future anomalies. A quiet payoff follows if the next dramatic fade arrives with fresh infrared glow from newly formed dust, and with a spatially uneven face the explanation again points outward. If instead the face stays uniform while the spectrum jitters, in ways tied to deeper layers the finger points inward. But there is a catch that keeps the intrigue alive. The layers inside Betelgeuse can change silently for years, because energy diffuses slowly outward, and the most honest early gossip may come not from light, but from particles that barely interact at all. Neutrinos, ghostly messengers from nuclear reactions, would surge in the final hours before collapse, and networks on Earth stand ready to notice. For now the network sleeps lightly. The scene widens once more. Betelgeuse does not float alone. It ploughs through thin interstellar gas, its past shedding building a bow shock like a ship's wave. That structure matters because it will shape the first bloom of a future supernova, turning the light curve and the color evolution into a conversation between blast and wind. The payoff is practical by understanding the shape and density of the material already around the star observers, can predict how bright and how prolonged the first days might be, and they can plan how to catch them. A final anchor closes the circle, a desert of space with an amber ember at its edge. The ember steady again, but no longer trusted, a reminder that wonder and vigilance can fit in the same frame. The handoff arrives softly if a living star can stage a vanishing act with dust and storms. What early tremor would unmistakably signal that the core, not the curtain, has begun to fail. To understand a star that startles the present, the narrative turns first to the past, because history narrows guesswork and sets the stakes for any future alarm. The consequence arrives. Early records across centuries reveal what counts as normal for Betelgeuse, so that when a light dips or a color shifts, observers can tell whether the star follows its known moods or steps beyond them. Evidence appears in the oldest catalogues where Betelgeuse already stands out a reddish lantern in Orion, that sailors, farmers, and court astronomers mark for its steady presence and gentle variability. Photometry, defined simply as the measurement of light, over time begins in earnest, with careful eyes, and patient notebooks, then grows into systematic practice as instruments become repeatable, and skies around the world become part of one conversation. A visual anchor settles on a wooden desk lit by lamplight, a ledger of winter night's ink noting the star's height and hue, frost ghosting the window while Orion climbs. The first payoff emerges in these ledgers, and early comparison charts Betelgeuse is variable, but it follows slow swells and shallows, brightening and dimming by amounts that, while noticeable to trained observers, remain within a range that repeats across seasons and decades. But there is a catch. The rhythm is not perfectly regular, and that irregularity is a clue, not a flaw. because it points to deep motions in the star's outer layers, rather than a clockwork metronome within. Light curve defined as the record of brightness, plotted against time, becomes the tool that turns memory into measurement. When stacks of such curves are layered, a shape appears long periods of rise and fall that sometimes beat together, sometimes drift apart. The so what is firm and calming. A star can wander within broad bounds for a very long while without reaching its end. Yet the narrative does not stop with paper. The 20th century adds photographic glass plates, a gallery of Orion frozen on emulsion, each exposure a square of night that can be remeasured with new methods long after the telescope is shut down. A second visual anchor appears as a shelf of labelled boxes in an archive cool and dim, where a researcher slides out a plate that shows Orion as a delicate scatter of grain Betelgeuse, a soft halo of silver. The payoff here is longevity with glass. The past is not rumour, but data and changes can be traced across generations, with the same stars used as yardsticks. But the intrigue deepens when community networks rise. The American Association of Variable Star Observers forms a living bridge between professional facilities and citizens with keen eyes and suitable instruments. Thousands of estimates become millions, and patterns that might have been missed in the noise stand out like footprints in fresh snow. The consequence is practical. When the Great Dimming arrives in late 2019, the association's long record makes the drop more than a surprise. It becomes a quantified outlier, a point far outside the envelope of familiar behaviour. Semi-regular variable defined as a star whose brightness changes with rhythms that shift in period and amplitude is the name that fits Betelgeuse in the taxonomy of variability, and the term matters because it signals both expectation and caution. Expectation because semi-regular giants breathe in layered cycles that overlap. Caution because some cycles may mask others, and the baseline can drift for reasons that are natural yet rare. A third visual anchor steadies the mind, a pinboard of printed light curves, month-stacked like terraces, the trace for Betelgeuse rising like a red tide, then falling like a slow sigh. The next payoff follows from comparing cycles. When multiple long periods beat together, they can create an unusually deep trough without any catastrophe, beneath a phenomenon that makes even a dramatic dimming an ambiguous messenger. But there is another catch. The same deep trough might, on some rare occasions, align with a fresh dust event or a large surface cell facing Earth, and then the visual effect becomes stronger than rhythm alone would suggest. Evidence appears in scattered historical notes of exceptional faintness, though none match the recent plunge, and in reports of colour shifts that hint at temperature changes, though modest ones. The so what is a measured warning. Outliers exist in the archival record, but they remain scarce, which makes any new one worth extraordinary scrutiny. Next comes the transition from eye and plate to precision instruments that still serve the same historical aim to keep the timeline honest. Photoelectric devices and later digital sensors remove much of the human bias in estimating brightness, and they allow observers across continents to work in a single scale. The result is a river of numbers that can be folded and compared not just year to year, but cycle to cycle. A fourth anchor image presents a small observatory dome under snow, its slit just open. A red star poised above a cup of breath turning to mist as the operator notes the time. The payoff is detectability. Small departures from usual patterns can now be spotted early, sometimes weeks before a dramatic change, and alerts can ripple outward to larger facilities that can scan for dust monitor surface patterns or take spectra that reveal motions in the outer layers. But there remains a deeper historical thread that tightens the stakes. Stories of stellar outbursts and sudden vanishings haunt sky traditions, yet the vast majority of bright familiar stars remain faithful companions through human ages. Betelgeuse occupies a rare middle ground, bright enough to feel personal, restless enough to invite myth, yet steady enough across centuries to be trusted as a seasonal signpost. The consequence is public meaning. When the star wanders, it moves feelings as well as numbers, so clear context drawn from history is not just academic. It is a way to guide wonder without fear. The final payoff of this section arrives as an operational rule refined by the long archive treat: every large change first as an atmospheric effect near the star, a dust veil or a surface storm unless independent signs point inward. Test with colour with infrared glow with the timing of known cycles. Only when those tests fail does the suspicion of deeper change rise. A last visual anchor holds the scene together, a quiet museum room where a child looks up at Orion charted on a century-old map, the same red shoulder glowing now in the winter sky outside. The soft handoff begins with a forward lean. If the past gives a ruler, the present must supply the scale, and that scale depends on exact distance, true size, and real brightness. Measuring those three sets the clock and the circumference of every later possibility, and that is where the story turns next. To weigh any future warning, the narrative must first set the scale of the star itself, because distance, true size, and total power decide how quickly changes matter and how loudly a finale will speak. The consequence is immediate and concrete. A nearby giant would brighten the sky far more at death than a distant twin, and a larger envelope reshapes both the signs that precede collapse and the way shock and light will later emerge. Evidence appears in the simplest ancient idea made modern: parallax, defined as the apparent shift of a nearby object when viewed from two separated points in Earth's orbit. Gaia, a space mission, refining stellar distances, has transformed this measurement into a survey of the galaxy. But Betelgeuse resists easy placement because its face is big on the sky, and its atmosphere is extended and restless. A first payoff arrives by facing that difficulty directly when a star looks like a disk rather than a point. The parallax signal mixes with surface motion and with the star's own walk through space, so careful, models must disentangle the dance to recover a clean distance. But there is a catch, and it keeps intrigue alive. The same winds and shells that make Betelgeuse fascinating also scatter light and pull the photocenter, the apparent center of light, away from the true center at times. The so what is simple and urgent. Any error here multiplies later, because luminosity defined as total power, emitted across all colors, grows with the square of distance. A visual anchor steadies the idea. Picture a wide ruler laid across Orion, the star set somewhere between the middle and the far mark, each millimeter shift on the ruler, turning into a vast leap in real space. Evidence grows as interferometry, already introduced as the linking of telescopes for finer detail sketches. Betelgeuse not as a dot but as a warm disk with mottled patches. Angular diameter becomes a second key, defined as how wide the star appears on the sky. Observers measure a small fraction of an arc-second a width. Human eyes cannot resolve yet enough for linked instruments to map. The payoff is tangible, with an angular size and a distance a true radius follows, large enough that if set where the sun sits, the star's outer layers would reach well into the realm of the inner planets. But there is another catch that demands nuance. Real starlight is darker near the edge of the disk, a behavior called limb darkening, defined simply as the rim appearing dimmer, because light there comes from cooler, higher layers. If uncorrected, limb darkening tricks are fit into stealing or adding size. The so what is a call for care. To know how big Betelgeuse is, one must know how its brightness falls from center to edge, and that fall shifts with wavelength. A second visual anchor holds the image of a slow-turning sphere bright in the middle, like a hearth coal and fading to copper near the rim. To tame such details, teams gather measurements across several colours of light. The Hubble Space Telescope probes the near-ultraviolet, the Very Large Telescope and other giant mirrors trace the red and near-infrared, and the Atacama Large Millimeter Array maps cool gas and dust around the star. A second payoff follows by fitting the limb darkening differently for each colour, and by comparing angular sizes at multiple colours, observers peel away the bias of a single band and arrive at a radius that is physically consistent with surface temperature and total power. Next comes temperature itself, a property with outsized leverage because a cooler surface means a larger size for the same total brightness, while a warmer surface would shrink the required area. Effective temperature needs only a short definition. The temperature a perfect radiator would have to emit the same power per area. Spectra. The fingerprints of light spread into colour give that temperature when matched to models that account for molecules seen in red supergiant atmospheres. The payoff is stability where it matters. While surface patches shift and plumes arise, the average temperature remains in a band that supports a large loose envelope rather than a contracting feverish shell. A third visual anchor keeps the numbers friendly. Imagine a lattice of light woven from countless tiny threads, each thread a colour band reporting on a different height in the atmosphere, the pattern holding even as some threads thicken and others thin. But there is a further refinement that changes expectations downstream. Gaia's distance combined with a corrected angular size and a well-measured temperature yields a total power that places Betelgeuse comfortably among luminous red supergiants, not at the brink of some unusual class. The consequence is steadying. The star is large and bright, but not so extreme that it must end tomorrow. It occupies a zone where changes can be bold without being terminal. Yet the intrigue deepens at the edge of the star where a molecular veil and dust formation make the measured disk look puffier than the true photosphere, the layer where most light escapes. Observers address this by fitting a core size and a separate halo, letting the halo carry the dust and the cool molecules, while the core marks the real surface for temperature and radius. The payoff is precision with a purpose. With a cleaner photospheric size, the breathing modes of the outer layers can be matched to the period seen in long light curves, and the match lets the interior density profile be sketched more honestly. This brings the narrative to a quiet but decisive stake. When the star's true radius and mass and total power are reconciled, the inferred internal structure sets the timeline for the current fusion stage, and for the time needed to exhaust it. The so what follows in plain terms. If the story says the star burns a layer that lasts for decades or centuries, then the next dimming is more likely a surface drama than a curtain rising on collapse. If the inner layer is late in a short phase, attention must sharpen. A fourth visual anchor clears the air a desert of space, with Orion rising a transparent cube drawn around Betelgeuse, its measured radius etched within the dust halo faintly glowing outside like breath on glass. But there is a catch: the size of the envelope itself. Convection, a gentle word for vast boiling drags patterns across the face and swells or compresses outer layers by a few percent, and those percent shifts alter angular size just enough to vex a single snapshot. The answer is cadence. Interferometers and spectrographs must revisit the star across months and years, building a movie rather than a portrait so that averages and trends stand clear of passing moods. The final payoff of this section is a practical readiness, distance size and total power. Now sit within credible bounds, tight enough that when a new anomaly arrives, the community can translate brightness and colour into real physical changes rather than guesses. The soft handoff points outward into space around the star because everything just measured lives inside a larger cocoon of wind and shock, and that cocoon will sculpt both the next surprise and the eventual display. To predict how the first flash will paint the sky, and how long the glow will linger, the neighbourhood of Betelgeuse must be mapped, and that is where the story turns next. The scale now widens beyond the star's limbs to the space it crosses, because the neighbourhood around Betelgeuse decides how its present winds flow, where its shed matter piles up, and how brightly a future outburst will play upon that material. The consequence is concrete. The same shock that one day will race outward will meet gas and dust already sculpted by motion, so the first days of light will be written by this environment as much as by the core. Evidence appears first in proper motion, defined as a steady drift on the sky, measured year by year, which shows Betelgeuse sliding through the local arm like a slow ember carried by a faint current. A first payoff arrives with a clear shape. Ahead of the motion lies a bow shock defined as the arcing front, where a star's wind collides with the oncoming interstellar gas, and that arc seen in infrared maps proves that the wind has been pushing for ages. A winter visual anchor fixes the picture Orion rising above a frost-dark field, the red shoulder moving imperceptibly, while an invisible crescent of warmed dust glows far beyond the reach of human eyes. But there is a catch that deepens the stakes. The distance between star and arc, the standoff distance, depends on three actors at once: the speed of the wind from the star, the speed of the star through space, and the density of the gas ahead. Change anyone, and the arc shifts, sometimes ruffling like a sail in uneven air. So what is immediate the shape of that arc, and the clumps within it become a forecast for how a future supernova shock will brighten, echo, and colour the sky in its first weeks. Evidence expands as telescopes gather the neighbourhood in multiple colours. In far infrared light, the arc shines where dust grains are gently heated. In ultraviolet light, a thin ribbon appears where faster particles and shocked gas glow. In radio light, molecules in the wind trace slow spirals and knots leaving the star. The payoff is a living map. The bow is not a perfect curve but a layered shell with ripples, fingers, and breaks, each recording a change in the wind or a knot in the interstellar medium, and each likely to seed later asymmetries in the display. A second visual anchor steadies the mind, a desert of space, with a faint copper ring ahead of a moving coal, and behind it a wake like a soft brush stroke where older wind trails downstream. But there is another catch. Betelgeuse likely carries a history of movement, perhaps a runaway origin from the Orion Association, and such a past would give it a space velocity that is not small. If the star once travelled faster, or through denser clouds, it could have left behind detached shells that now sit at staggered distances. The so what becomes layered time when bright light later sweeps outward. It could paint those shells in sequence, producing light echoes separated by months or years, each echo a new window into the explosion geometry. A quiet payoff follows from the physics at the arc, where ram pressure, a simple push from relative motion, balances the push of the stellar wind. The arc stands. Measure the curvature and brightness, and the push on each side can be inferred, which in turn constrains the present mass loss rate. That rate matters now and later now because it sets how quickly the circumstellar cocoon thickens. Later because a denser cocoon means a brighter and more structured early light curve in the event of a supernova. A third visual anchor leans close. Imagine a translucent shield ahead of the star, its edge scalloped by small waves, with filaments fluttering like banners where instabilities nibble at the boundary. But there is a further subtlety. The wind is not perfectly smooth because giant convective cells on the surface loft material in plumes, and those plumes can seed dust that survives, and drifts outward along preferred directions. Over time, preferred directions become lanes of thicker material in the broader wind which then feed the bow unevenly. The so what is pattern. Recognition. An asymmetric wind now implies an asymmetric response later, so observers already know to watch for lopsided brightening and directional radio flashes when the blast meets these lanes. Evidence points to this complexity in images that show arcs within arcs, and faint linear features bending with the motion, as if the traveller carried a woven mantle that frays and reforges as it goes. A fourth payoff resolves a lingering ambiguity from earlier dimming when the star sheds a large plume. The plume's path and fate depend on wind speed and ambient pressure, which means that dust events are not just surface affairs but neighbourhood stories, and their clearing times teach the density of space around the star. A fourth anchor image brings Orion's larger frame into view. The Orion complex of bright young stars and molecular clouds lies nearby on the sky, but Betelgeuse sits in front of most of that cloudwork shoulder lifted from the mist. The local arm here is not uniform. Pockets of thinner gas and patches of dust thread the region, like weather in a high desert. The consequence is practical. A blast wave leaving Betelgeuse in the future will run into a patchwork, so the light that follows will rise and ripple rather than bloom, evenly offering a chance to read density like tree rings. But there is a catch that keeps intrigue intact. The bow shock appears stable over years in broad surveys, yet small changes tempt interpretation, and teasing real motion from instrument differences demands patience. The what turns operational continued imaging with consistent methods locks down whether the arc advances, retreats, or roughens, and that trend becomes a daily forecast for the next decade rather than a single snapshot. Evidence thickens as different observatories chart complementary layers. The Wide Field Infrared Survey Explorer outlines warm dust in the arc and in a faint trail downstream. The Herschel Observatory lays finer structure across the crescent, revealing nested shells as if the star breathed harder at intervals. The Atacama Large Millimeter Array maps molecules in the inner wind, linking stellar outbursts to features far out. The payoff is orchestration. The neighbourhood can be measured as a system from face to plume to wind to bow, allowing models to practice the future play before the curtain truly rises. A final anchor image returns to the human sky. The belt and sword hang like a ladder of blue sparks. Above the left shoulder, the red star steadies after the great dimming. Yet around it, unseen invisible light, lies a fragile architecture of arcs and lanes that will decide the choreography of any future spectacle. The soft handoff brings the attention inward again to understand how those lanes are laid down the surface. Where the wind begins must be read with care because continents of brightness, star spots and slow pulsations are the hands that stir the flow. The narrative now turns to the face of the giant where boiling cells and moving patches write the weather that fills the space beyond. The face of Betelgeuse is not a smooth lantern but a restless landscape, and what happens there sets the wind that fills the space around it and shapes every later sign of change. The consequence is direct vast convective cells and dark star spots can dim the star seed dust and redirect outflow, so a sudden fade at Earth may be weather on the surface rather than trouble in the core. Evidence appears first through interferometry, defined as linking telescopes to act like one, and resolve fine detail which sketches a mottled disk where bright plateaus and dusky basins drift like continents of heat. A first payoff arrives with clarity when a bright plateau faces Earth. The star looks slightly hotter and larger. When a dark basin turns into view, the light slackens and the apparent size can shrink, mimicking a deeper change. But there is a catch. These features are not small freckles. Each cell can span a fraction of the entire disk, rising slowly, cooling as it spreads, then sinking in a cycle that lasts months. The so what is reassuring yet sobering the surface can produce major photometric swings without any crisis inside, but those swings can also loft matter that becomes dust, which then compounds the dimming. A winter visual anchor steadies the idea, a slow-turning sphere, the colour of banked embers, its face patched with moving islands of copper and umber edges feathered where heat ebbs into space. Evidence deepens when spectrographs spread starlight into its fingerprints and reveal that lines from certain atoms shift back and forth across the face. Doppler map, defined simply as a picture of motion, drawn from line shift, shows upflows that are broad and gentle, and downflows that are narrower and faster, a hallmark of convection on a grand scale. The payoff is mechanism over myth. A star like Betelgeuse boils, and boiling creates texture. Texture seeds mass loss, and mass loss feeds the dust veil that sometimes drops across our line of sight. Next comes spectropolarimetry, defined as measuring how light waves line up, which can trace magnetic fields that lace the surface. The fields appear weak compared to compact stars, yet they matter because they corral upwellings and may anchor star spots regions cooler and darker, where rising hot gas is hindered. But there is another catch. Magnetic patterns wander and flicker, and separating their effect from pure convection requires long campaigns under steady calibration. The so what becomes operational only by revisiting the face across many rotations can observers tell which dimples are magnetic scars and which are mere weather. A second visual anchor gathers the instruments into one scene. The Very Large Telescope combs the red light for structure. The Atacama Large Millimeter Array maps cool gas in arcs just off the limb. The Hubble Space Telescope picks up ultraviolet traces of hot patches, and together they sketch a breathing skin over a deep furnace. A second payoff follows from this orchestration when bright ultraviolet knots coincide with outward streaming gas in the millimeter, maps the link between surface heating and mass ejection, becomes firm, and future dimmings caused by dust can be forecast as the plumes travel outward and cool. But there is a catch that safeguards humility. The star does not show a simple rotation period like the Sun. Instead, the surface appears to tumble in slow, uneven sways, so that features drift in longitude and latitude without a stable clock to reference. The so what tightens changes must be tracked by pattern rather than by rotation, which means models must follow fluid parcels, not just spots on a sphere. Evidence appears in time series where the bright plateaus split, merge and migrate, while the darker regions wax and thin as if a tide of heat shifts under a thin crust. The third payoff arrives in predictive power. When a dominant plateau approaches the limb, the overall brightness dips predictably, and when two basins align, the dip can become pronounced even without new dust. A third visual anchor keeps the picture tangible, a lattice of light flowing like slow lava, with cooler veins widening and narrowing across the face, while small jets flicker above the rim. The narrative now threads the connection between the face and the wind. Mass loss defined as the steady escape of gas from the star begins where convective upflows cool enough to let molecules bind and grains condense, which increases opacity and lets radiation push on matter more effectively. That simple chain makes the surface a switchboard for the entire circumstellar cocoon. The payoff is practical. By reading the surface pattern, observers can guess which longitudes will thicken with dust next season, and they can point infrared instruments to watch the birth of the veil before it slides across the line of sight. But there is another catch that guards against overconfidence. Plumes sometimes rise and fail, raining back before grains can form. Other times a plume escapes, but the wind shear shreds it into filaments that dim only a portion of the disk, creating a partial eclipse effect rather than a global fade. Though what insists on nuance, a deep dip may be a patchwork of local curtains, not a single global shroud, and the correction time depends on how those curtains drift and disperse. Evidence accumulates in resolved images that catch asymmetric halos close to the limb, and in spectral lines that split into multiple components, each one tracing a separate stream. The fourth payoff gives a rule of thumb if a dimming event grows, while infrared emission from fresh dust also grows, and high-resolution images show a lopsided face. Then the cause is almost surely an outward plume and a local dust cloud. If instead the spectrum hints at coherent inward or outward motions across the entire face with little new dust, the change may trace a deeper pulsation. A fourth visual anchor returns to the human sky. Orion hanging above rooftops after midnight, a reddish coal steadier now, while unseen likes of smoke drift just beyond sight, already reshaping what the next season will show. The narrative circles back to stakes. A surface that can sculpt the wind and conjure curtains explains much of Betelgeuse's restless brightness, and that explanation lowers false alarms. Yet the same surface acts as a sounding board for the interior, because pulsations that begin deeper must move the skin, and when the skin moves in particular ways, observers can hear the drumbeat of layers beneath. The soft handoff turns toward that inner rhythm. If the face is the weather, the pulse is the tide. And when the tide changes tempo, the whole star hints at where it stands in its long descent toward an iron heart. The next section therefore listens to the beating patterns that time the breathing of the giant and asks what a shift in rhythm would truly mean. Rhythm is the language by which a swollen giant announces its inner weather, and in Betelgeuse that language is written as slow breaths of light and colour that rise and fall over months and years. The consequence is immediate and sharp. If the tempo changes beyond its long-recorded range, the suspicion must pivot inward, because a shift in rhythm can signal restructured layers instead of surface tricks. To begin pulsation needs a small definition. It is the global in and out motion of the outer layers, like a lung that expands and contracts under the push and pull of pressure and gravity. Historic observations show at least two main cycles in Betelgeuse, one long and one shorter, and these cycles do not tick like a metronome but drift slowly, as the outer envelope responds to convection and to changing mass loss. The first payoff arrives as insight rather than alarm. A semi-regular light curve is not confusion but information, because the exact spacing and strength of its crests and troughs encode the density of outer layers, the stiffness of the envelope, and the way energy leaks outward. A winter visual anchor steadies the idea, a slow turning sphere seen as if through a thin veil, its redness deepening and easing with the patience of a tide, not with the shock of a storm. Evidence grows as observers feed the star's light into instruments that can measure brightness with clockwork cadence night after night. The Transiting Exoplanet Survey, Satellite, a sky-scanning mission that catches tiny dips when planets cross stars, also watches giants breathe returning streams of points that reveal tempos too subtle for casual eyes. Period beating requires only a short image. When two rhythms of similar length overlap their peaks, sometimes add and sometimes cancel, producing seasons of unusually high or low brightness, without any crisis beneath. So, what is practical by fitting 2 or 3 principal periods, and allowing small drifts the community can forecast, where the next deep trough might fall, and can be ready to test whether that trough grows the fingerprints of dust or stays clean as a pure pulse. But there is a catch that feeds the intrigue. Pulsation modes come in types radial, where the whole shell rises and falls together, and non-radial, where different zones move in counterpoint. Distinguishing them from light alone is hard when a star shows a resolved face and a restless surface. A second payoff answers that difficulty with a method's spectra. The spread of light into its colours show lines that wiggle in wavelength when layers move toward or away from the observer, and by comparing those wiggles across lines that form at different depths, observers build a vertical map of motion that separates a global push from local winds. A fresh visual anchor fixes this scene a lattice of thin lines across a rainbow. Each line nudged a breath to the left or right, a quiet seismogram written in colour. Next comes phase, a small concept that yields leverage. Phase is where one sits within a cycle, and when the phase of the short rhythm runs in step with the bright or dark plateaus on the face, surface weather dominates. When the phase drifts independently of visible patches, a deeper pulse is speaking through the noise. The so what tightens into a testable rule. If the timing of the dip matches the predicted joint phase of the principal periods, and if the spectra show symmetric in and out motions, the event is a tide. If the timing strays and the motions skew or split, the tide is being nudged by new internal architecture. Evidence appears in long baselines where one of the main periods lengthens subtly across decades. That slow lengthening is not a random walk, but a sign that the outer envelope has cooled and expanded slightly on average, likely a steady mass loss, thins the layers and alters how sound travels through the star. The third payoff is a clock that whispers, even if collapse is not near the envelope, is aging in a measurable way, and that aging shifts the music by small amounts that instruments can resolve years before the eye notices. Another visual anchor drifts into view as a slow wave travelling across a sea of light. The wave changes just enough each season to keep the shorelines of maxima and minima from landing at the same bays. Yet there is a catch that guards humility. Instrumental cadence can imprint false periods, and seasonal gaps leave aliases, ghost rhythms that masquerade as real. The so what is procedure, not poetry. Data from professional networks and from the American Association of Variable Star Observers must be stitched with the regular streams from space missions, and the combined timeline must be checked against known sampling biases before any claim of new rhythm is believed. When that procedure holds, a fourth payoff emerges. The star's light can be decomposed into a few principal components that each carry a physical meaning, one tied to the main breathing of the envelope, one perhaps tied to a deeper second overtone, one tied to surface cells rotating slowly in and out of view. With that decomposition in hand, a near-term forecast becomes possible. Observers can announce that a particular month range is likely to host a deeper than average trough or a brighter crest, and they can call for complementary observations that will confirm whether dust forms or whether the change remains purely dynamical. A winter visual anchor sets that plan against the sky, Orion rising over a line of snow-topped roofs, a calendar page pinned nearby, marked with a window of expected change, instruments cued to listen. The narrative presses inward another step because pulsation is not only a surface breath. Deep inside, where the energy of fusion supports the weight of layers, neutrino cooling, defined simply as loss of energy, through neutrinos that rarely interact, begins to sap heat long before collapse. When that cooling bites harder, the envelope may respond by shifting period or amplitude as the star adjusts its structure. So what is a hint toward premonition? A slow coherent drift of period accompanied by changes in spectral line depths across many elements could mark a deeper energy balance shift, and that would justify a heightened watch for other messengers. But there is another catch that keeps certainty at bay. The envelope is a tangle of convection and waves, and a drift can also arise from the slow dance of surface cells and mass loss patterns, which means that only a convergence of light, colour and velocity signs repeated across seasons can push an interpretation inward. The section closes with the final payoff that sets up the next act. By mastering the star's tempo map, the community knows when to look for the outward veil that can make a deep trough truly dramatic. When the predicted low phase approaches, infrared eyes turn to the regions just off the limb to watch for cooling plumes and nascent grains. The soft handoff follows naturally if rhythm sets the schedule, dust writes the spectacle, and the next section turns to how dust forms thickens and clears, and how a vanishing trick can mislead even while it tells the truth about the star's living breath. Dust is the star's simplest magic, and its most convincing disguise, and in Betelgeuse that magic can make a bright shoulder of winter seem to vanish without the core changing pace. The consequence is immediate and calming. A steep drop in visible light can arise from a veil thrown just above the surface, a local cloud of tiny grains that cool and scatter light so the sky can darken while the engine within continues its long patient work. To begin, dust needs only a short definition. Dust consists of solid grains condensed from cooling gas, each grain small enough to ride the wind and large enough to bend and block light. Evidence appears when ultraviolet and infrared instruments tell different stories at the same time. Visible light falls away, yet infrared glow from the immediate neighbourhood grows a sign that fresh grains are absorbing starlight and re-emitting it as gentle warmth. The first payoff arrives with a picture that feels both ordinary and cosmic. A bright hearth throws sparks into a cold room and a breath of smoke drifts between the fire and the eye, muting the flame while the room grows warmer where the smoke hangs. But there is a catch that deepens the puzzle. Not all grains are equal. Species such as silicates and alumina condense at different temperatures and distances, and the size of a grain tunes how it scatters colours. The so what is diagnostic power by sampling light across many wavelengths. Observers distinguish a change caused by new dust from a change caused by a cooler surface, because dust leaves a spectral fingerprint of slopes and bumps that a mere temperature dip cannot mimic. A winter visual anchor fixes the method. James Webb maps warm dust just off the limb in bands that glow like copper filigree. The Atacama Large Millimeter Array traces cooler molecules coasting outward, and the Very Large Telescope sees the face itself mottled where plumes rise. Together they show a sequence a hot patch lifts. The gas expands and cools molecules bind, and grains form along a path that arcs away from the star like a slow splash. The second payoff follows from timing. When a dimming begins at Earth, infrared brightness in freshly formed dust usually peaks slightly later, because grains need time to grow and to move into a position where their combined veil intercepts more of the star's face. This lag, measured and compared with the breathing phase of the star, is a clean signature of a dust event rather than an inward failure. Yet there is another catch that keeps the narrative honest. Optical depth, defined simply as how opaque a layer is to light, depends on both the amount of dust and how it is arranged. A thin curtain across the whole disk can dim uniformly, while a thick patch across one quadrant can create asymmetry that changes as the star turns and as wind shear reshapes the clump. So what is directional behaviour-resolved images sometimes catch a crescent of extinction across the stellar face, and that crescent explains a light curve that falls fast, stalls, and then deepens as the geometry shifts. A second visual anchor steadies the imagination, a slow, turning sphere half-veiled by gauze, the uncovered side glowing like an ember through clear air. The covered side bruised and faint where the gauze thickens. Evidence grows sharper when polarimetry, a technique that reads the preferred orientation of light, detects the scattering telltale of small grains. Increases in polarized light at certain angles mark the presence of new dust and help place it in 3 dimensions around the star. The third payoff is triangulation combined polarimetry with infrared color changes and with interferometric asymmetry, and the veil is no longer guesswork but a mapped feature with size, position, and likely composition. But there is a catch of timescale. Grains are transient this close to a giant. Starlight warms them, radiation pressure pushes them, and shocks in the wind can shred clumps into wisps. Clearing therefore follows a 2-step dance. First, the densest part of the cloud shifts off the direct line of sight, lifting the deepest dimming. Second, the diffuse remainder thins as grains drift outward and cool so far that they no longer affect visible light. So what is predictive by watching the speed of that lift in different bands? Observers estimate the wind speed and the grain sizes, turning a vanishing act into a measurement of the neighborhood. A third visual anchor gathers this into one memory. Picture a lattice of light brightening behind a thinning fog, the fog patch sliding to one side while a pale afterglow persists in the warmth of the surrounding air, then finally fading as the room clears. The narrative presses the mechanism one level deeper. Nucleation, defined as the first step where molecules cluster into seed particles, needs the right mix of cooling density and chemistry. In red supergiant envelopes, alumina can seed first very close to the star, while silicates condense farther out where the gas has cooled more. When a large convective cell lofts a dense parcel, the parcel travels through these thresholds and leaves a trail of mixed grains, each layer born at its preferred altitude. The fourth payoff is a layered veil. Observers sometimes see both very hot dust close in and slightly cooler dust farther out in the same episode, a stratification that matches the theory of stepwise condensation. And that explains why some dimmings have shoulders and plateaus rather than a clean V-shape. But there is another catch that teaches humility. Not all dimming requires new grains. A pre-existing diffuse halo can be reshaped by a fresh wind pulse into a temporary overdensity along the line of sight, a lensing of extinction without a large change in total dust mass. The so what becomes a caution only when new infrared emission rises and when grain signatures strengthen is it safe to declare fresh formation. Otherwise the culprit may be rearrangement rather than growth. Evidence from archival episodes shows both patterns, and this diversity tells that Betelgeuse is a storyteller with more than one trick. A fourth visual anchor returns the eye to the wider Orion frame, the belt star's cold blue, the sword faint and misty, the red shoulder steadying after its stumble, while an unseen cloud moves away like a slow puff in the dark. The stakes align with safety. Dust events can be dramatic, public, and harmless to Earth, yet they also announce vigorous mass loss that feeds the cocoon a future blast will use as canvas. The consequence is scientific urgency, not dread. By counting dust events, weighing their masses, and mapping their directions, the community writes the boundary conditions for any later explosion model. Knowing where the thick lanes lie tells where a shock will light up first, and knowing typical clearing times helps calibrate how quickly observers must move when a new plunge begins. The final payoff of this section is a firm operational lesson. Treat any sudden fading first as a dust curtain test with wavelength polarization and resolved shape, and if the curtain holds, use it to measure the wind. Only when the curtain fails to appear should attention pivot inward to structural change. The soft handoff follows naturally from that pivot. If dust writes the spectacle outside, the interior writes the schedule. The next section steps through the furnace within a layered set of fusion shells that slowly build an iron heart, because the true clock for any finale is kept not by the veil, but by the core. Wind is the quiet author of the space around Betelgeuse, and over centuries that wind lays down a layered envelope that will one day decide how the first light of an explosion rises, ripples and fades. The consequence is exact and predictive density today becomes drama tomorrow, because a thicker shell will turn a newborn flash into a longer, brighter pulse, while a thinner shell will let the light climb fast and fall like a bell struck in clear air. Evidence appears in broad surveys that reveal arcs and shells wrapped around the star, each a fossil breath from an earlier season of stronger or weaker outflow. The first payoff arrives as a map the eye can keep near the star. A warm inner shell glows in mid-infrared light. Farther out, a cooler envelope shows itself in millimeter lines from drifting molecules. Farthest, the bow shock marks where the personal weather of Betelgeuse meets the faint wind of the galaxy. But there is a catch that deepens the stakes. The wind is not constant, but breathes with the star's own cycles and with convective storms that feed it. The so what is pattern over uniformity rings arcs and clumps, record a history of surges and lulls, so any future shock will travel through a three-dimensional memory rather than a smooth fog. A winter visual anchor fixes the picture, a desert of space, the red ember at centre, and around it a faint onion of shells, some crisp, some shredded, their edges scalloped, where small waves have nibbled for years. Next comes speed, a small concept with large consequences. The outflow creeps at only a few tens of kilometers per second, slow enough that features close to the star hold the freshest news about the last few years, while remote arcs remember decades. The payoff is a clock keyed to distance by measuring how far a shell sits, and how quickly similar material drifts now. Observers date the breath that made it, placing recent mass loss into a timeline that can be tested when the next dimming or brightening occurs. Yet there is another catch. The wind carries not only gas but grains, and radiation pushes grains more strongly than gas, so dust can run ahead and drag some gas with it, leaving pockets where composition and density differ from place to place. The so what is mixture sensitivity spectra taken with the Atacama Large Millimeter Array show some lanes rich in molecules and others poor, while infrared images from the James Webb Space Telescope show ribbons of dust that curve and fork, promising that a later shock will paint in stripes rather than in a perfect ring. A second visual anchor leans in picture, a slow snow of ash blowing into a field. The ash settling in drifts behind small obstacles and in shallow bands, where the breeze shifts a pattern only visible when moonlight glances across it. Evidence tightens as line profiles reveal how the wind accelerates. Close to the photosphere, the gas is almost still. Within a few stellar radii, lines from molecules and simple atoms widen and shift, telling that radiation pressure and collisions have brought the wind to its cruising speed. The second payoff follows from this acceleration zone. Because dust seeds near the star and couples to light early small changes on the face can alter the push within this zone, imprinting a signature that can later be read in the spacing and thickness of inner shells. But there is a catch of geometry. The wind does not leave uniformly from all longitudes. Preferred outflow lanes set by the largest convective cells and by gentle magnetic guides tilt the density pattern, thickening some sectors and thinning others. The so what is a symmetry with a purpose. When a future shock exits the star, it will move faster into thin lanes and slower into thick ones, creating a light curve with small shoulders and colour changes that trace direction as well as time. A third visual anchor steadies the idea, a slow turning sphere exhaling into a folded cloak. The cloak seems thicker than its panels, so that a gust finds easy passages and hard walls as it spreads. Now the narrative joins this shaped envelope to the physics of a future outburst, staying grounded in what can be measured today. Shock breakout, defined simply as the instant when a buried shock reaches the surface and light surges free, will be followed in minutes to hours by a blast wave meeting the inner wind. If the inner density is high, that meeting converts more kinetic energy into heat and light, boosting ultraviolet and X-ray glow, and delaying the moment when the visible light peaks. The payoff is a forecast that a schoolchild can follow. Thicker nearby air equals a longer sunrise for the supernova. Thinner air equals a bright, sharp dawn. But there is another catch that keeps the work careful. Interaction with circumstellar material defined as the shock heating and compressing the wind it meets can mimic some signatures of an intrinsically brighter explosion by adding its own light, so observers must separate these effects by watching radio and X-ray bands as well as visible light. The So What Is Strategy radio arrays will chase the earliest days for proof of electrons whipped to high speeds, where the shock plows, while the James Webb Space Telescope and large ground telescopes will watch for fresh dust, forming in the cooling wake a secondary veil that can turn the light redder after the first rise. A fourth payoff emerges from the bow shock itself. The curved wall ahead of the star sets a frontier. Months or years after the first light, when the main blast arrives there, it will spark a delayed glow or a series of light echoes as reflection off dust sheets sends time-shifted copies of the event back toward Earth. Those echoes will trace the shape and tilt of the bow and will allow distances within the neighborhood to be measured with crisp geometry. A fourth visual anchor expands the scale. Orion's figure faintly traced across a black field, a thin arc ahead of the red shoulder like a shoreline, and beyond that dark water waiting for the wave. Evidence also points to fossil shells behind the star along its path where past winds met differing densities and left detached arcs. The consequence is a long afterword to any explosion, a sequence of re-illuminations that can extend the learning years beyond the day of the blast. But there is a final catch that returns to the present. Measuring this architecture demands consistency over time. Small differences in instruments can masquerade as motion or thickening unless the same bands, the same filters, and the same calibration are applied season after season. The So What becomes a promise of readiness rather than a prediction. By maintaining a stable multi-wavelength campaign, now the community can turn the eventual light show into a laboratory where every rise and ripple reads back the exact density along the shock's route. The section closes with a quiet payoff that also seeds the next turn inward. The envelope can tell how the spectacle will unfold, but only the core decides when the curtain lifts. To judge where that clock stands, the narrative must enter the furnace itself and walk the shrinking ladder of fusion shells down to the boundary, where iron will one day halt the fire and where silence falls before the last loud release. Inside Betelgeuse lies the only clock that matters for the ending, a layered furnace where each burning stage writes a shorter chapter than the last, so the consequence is stark understanding. The order and tempo of these layers turns fear into watchfulness, because a restless surface can persist for decades, while the core advances through phases that may last only years or even days. To begin, the narrative walks down the ladder of fusion shells, simple in concept though grand in scale. A star-born massive spends its long early life burning hydrogen into helium at the core. When that fuel wanes, fusion moves outward into a shell, and the core contracts and heats until helium fuses into carbon and oxygen. Later, deeper come stages where carbon burns to neon, and magnesium then neon to oxygen to silicon and sulfur, and finally silicon to elements near iron. A first payoff arrives with a clean rule that shapes expectation. Each step burns faster than the one before, because higher temperatures allow reactions that release less energy per unit mass, so time to exhaustion shrinks with every rung. But there is a catch that drives home uncertainty. Observers cannot see the core directly. They infer its state from surface motions, from changing periods, from overall luminosity, and from models tuned by measurements of mass and radius. What is procedural, the path is known. The step we are on is less so, and the proper posture is readiness backed by tests, not alarm driven by guesswork. A winter visual anchor brings the unseen into a simple picture. Imagine a nested set of glowing shells inside a dim red lantern, each inner shell hotter and thinner, the outer envelope loose and deep like soft cloth wrapped around hard iron tools. Evidence that the ladder is being climbed arrives in the measured mass loss and in the pulsation modes that fit an extended envelope hallmarks of a core that has already burned hydrogen and helium and that now likely sits in one of the advanced stages beyond carbon. A second payoff enters through a quiet actor neutrino cooling, defined as energy carried away by nearly non-interacting particles that stream from the hot core long before collapse. When neutrino losses steal heat, the core contracts slightly, and heats further, accelerating the next burning stage, and that acceleration shortens time left, even as the outer envelope appears little changed. But there is a catch set by physics that refuses spectacle until the end. The reaction chain that leads toward iron increases the central temperature to fantastically high values, without a sudden visible signature at the surface, and the pressure support within the core begins to rely in part on the quantum rule that resists squeezing electrons too close, a concept called degeneracy pressure, that needs no more than this, a pressure born of crowded states rather than heat. What is tension without a show, the clock can speed within while the skin still breathes its patient tide. A second visual anchor steadies that idea with an image the mind can hold, a slow, turning sphere whose face smoulders gently while deep inside a bright bead grows hotter and more compact like a coal, forming within a larger ember. Evidence from theory aligned with observation suggests that the final pre-collapse stage, silicon burning to elements around iron, lasts from days to weeks in the most massive giants, and that the silicon shell grows as ash of iron group elements accumulates in the core. The third payoff is a promise of an early messenger. When the core finally breaks equilibrium and collapse begins, a flood of neutrinos will leap outward for a few scant seconds before any light changes, and detectors on Earth will notice that whispering storm. Yet there is another catch that matters for today. Before that final surge, smaller changes in neutrino output during late burning are too faint and too steady to stand clear of background, so no instrument can presently tag a specific year from neutrinos alone. What is a division of labor. Light and velocity maps track the envelope for hints of structural adjustment, while neutrino networks wait only for a decisive shout, not for a murmur. A third visual anchor sets the sky against the laboratory Orion. Above a dark ridge and far below ground, quiet tanks of clear liquid, watching for rare flashes as ghostly particles pass. The narrative turns to how an advancing core might tug the outer layers into changed behavior that tools can sense. As energy generation shifts inward, a neutrino cooling deepens the ceiling that the envelope leans upon, settles, altering how waves reflect and how the skin breathes. Period drifts and amplitude changes appear as small yet coherent signatures across cycles, a tide chart that begins to slide in a new direction. A fourth payoff emerges from matching those drifts with measured mass loss. If the envelope becomes slightly more extended and the main period lengthens while mass loss rises, a consistent picture forms of a star moving deeper into late burning without imminent collapse. But there is a catch set by convection's unruly hand. Large cells in the envelope can mimic period changes by transporting heat unevenly, and they can reshape the rhythm without any core driver. The so what returns to method only a convergence of independent signs deserves weight, so observers require period drift across many bands, spectral line changes from multiple elements at different depths, and mass loss variations seen in molecules and dust before claiming a structural shift forced from within. A fourth visual anchor helps hold the many threads together. A lattice of light traced against a graph, the peaks drifting gently apart year by year, while a faint haze above the line grows thicker, a quiet balance tilting. The story approaches the edge where the furnace will fail. Iron does not release energy by fusion in the conditions of a stellar core, so once iron and its neighbours dominate adding heat, by further fusion is not possible. The core then faces gravity unopposed by new fire, and when it contracts enough to break the support of crowded electrons, collapse begins in a rush. The consequence is both grand and humane. Grand because a shock forms and in moments will race outward to transform a red star into a day-bright lantern. Humane because this drama will play at a distance safe for Earth, turning fear to awe. Yet a catch remains even here. The precise trigger depends on core mass, on electron capture, on certain nuclei that reduce pressure, and on the interplay between neutrino losses and heat flow details that remain under study in models anchored by sparse direct data. The "so what is humility with discipline predictions" must be phrased as likelihoods and ranges, not dates, and the proper preparation is to refine the watch list of early signs. The section's final payoff turns to that list. Before light changes, a burst of neutrinos will sound. Minutes to an hour later, shock breakout will bathe the star in a brief high-energy flush. Then visible light will climb, shaped by the inner wind. The soft handoff now invites the next turn, since the core's ending will first speak through neutrinos. The community's readiness depends on the networks that listen, the alerts they can send, and the choreography of telescopes that can turn at once toward the red shoulder when that whisper arrives. Countdown clues arrive as quiet signatures before any flash, and for Betelgeuse, the earliest and most decisive messenger will not be light at all. So the consequence is practical and large. If the first signal reaches Earth in particles, almost no matter can stop. The world can know before the sky changes and can turn every eye toward Orion in time to catch minutes that never repeat. Neutrinos defined simply as nearly massless particles that interact only rarely stream from a core when the last burning stage falters and when collapse begins, and those particles pass through rock and ocean as if through air. The first payoff is a timetable. The mind can hold a burst of neutrinos will arrive tens of seconds before shock breakout. The brief moment when a buried shock wave reaches the surface and releases high-energy light, and minutes to an hour before visible light swells. But there is a catch. Background signals from natural radioactivity and from cosmic rays can mimic small flurries of events, so alerts must rise only when many detectors hear the same whisper at the same time. The Supernova Early Warning System, a global network that links neutrino observatories, exists to solve that problem by comparing upticks instantly and sending a notice within moments when a coincidence stands out above chance. A winter visual anchor frames readiness far below mountains and ice sheets, quiet tanks of liquid and forests of light sensors wait in dark caverns while above on a frost-hard night, Orion tilts toward the meridian and the red shoulder glows as if unaware. The second payoff turns to how that message triggers a dance. When the network sounds wide-field instruments that sweep the sky, can begin rapid patrols at the coordinates of Orion, while narrow-field telescopes that need precise targets can ready sequences to catch the first minutes of light once a coordinator narrows the exact position. But there is another catch that sharpens the stakes. Neutrinos carry little direction information in most detectors, so early on the alert will name only a region, not a pinpoint. The "so what is choreography?" Robotic surveys must scan radio arrays, must begin to listen for the earlier signs of electrons whipped to high speeds by shocks entering the inner wind, and space-based instruments sensitive to ultraviolet and X-ray light must prepare to pivot the moment a brightening is found. A second visual anchor fixes that pivot a control room glows with soft screens. A row of sky maps slides across a red circle encloses the shoulder of the hunter, and scripts launch to cue shutters, pointings and exposure times measured in seconds. Evidence from past supernovae in other galaxies shows that shock breakout can be brief and bright in high-energy bands and easily missed if eyes arrive late. The third payoff is practical instruction. A neutrino alarm buys minutes that transform a lucky catch into a planned observation of the first light, the moment when theory has least guidance and most to gain. Yet, there is a catch tied to caution. Betelgeuse is not guaranteed to be the source of the next alert, and the network will not name a star until light confirms the location, because false precision breeds confusion. The so what becomes patience under urgency observers must prepare sequences where discovery images and confirmations alternate quickly, so that the community can lock onto Betelgeuse and agree within moments. Next comes the second class of countdown clue, subtle precursors in light and line that may precede the final rush by days or weeks. Spectral lines formed in the outer atmosphere can show jitter that grows in amplitude, a sign that waves from within are jostling the skin as energy transport shifts. A fourth payoff enters as a watch list that any observatory can use even before a neutrino burst, coherent changes in multiple lines, at different depths, a small but sustained rise in high-frequency light from heating near the surface, and hints of new ionized species that mark elevated temperatures can add to a case that the star is entering a new internal regime. But there is another catch, and it is familiar. Surface storms and dust veils can mimic some of these behaviors, so the list must be coupled to infrared imaging that shows whether fresh grains are forming, and to resolved views that test for a symmetry across the face. What is a two-key system only when both keys turn 1 for light behavior, inconsistent with dust or with ordinary pulsation, and 1 for a neutrino surge does the door to a true countdown open. A third visual anchor grounds that procedure in the sky. Orion rises over a dark ridge. A cluster of small domes points upward, and in a lab beneath the hill, a silent board shows a rising trace from a neutrino detector, while outside a small robotic telescope begins its cadence of short repeated exposures. The narrative then turns to communications because clarity in the first hour matters as much as sensitivity. A neutrino alert must translate into a public and professional message that states distant safety and expected timing in plain language, since a red star well known to anyone who steps outside will bring attention far beyond the observatory world. The fifth payoff is social stability in the service of science. By making clear that Betelgeuse sits far enough away to be a spectacle and not a hazard, the community preserves trust and keeps bandwidth focused on data rather than rumour. Yet there is a catch in the torrent that follows. Tens of thousands of observations will flood servers, and without agreed formats and timestamps, the early minutes can blur. So what is preparation now? Teams rehearse data pipelines, define common time standards, and create shared portals where observations appear in order and with basic quality flags so that modelling can begin while the light is still climbing. A fourth visual anchor returns to the human scale. A small backyard instrument hums under frost, while many time zones away a giant mirror opens. Both write to the same stream, both matter, both find a place in the first global draft of a nearby star's transformation. The section closes with a final payoff and a soft turn. The earliest clues from neutrinos to the first rise of light do more than announce an event. They carve the explosion into time slices that separate the core physics from the conversation with the wind, yielding a blueprint for how to read everything that follows. If the beginning is captured, the middle and end become legible. The next section therefore walks through the first hours and days after collapse, when silence becomes a flash, and a red ember becomes a small sun in winter, and it sets the sequence that will let observers know, minute by minute, that the finale has truly begun. When collapse begins, the change from silence to signal is sudden, layered and legible, if the order is kept in mind, so the consequence is clarity. Amid awe, by reading the first minutes and hours in sequence, observers can separate the cry of the core from the roar of the wind and learn both. The moment of core failure is inward and dark. In a breath, the central region gives way, matter rushes inward, and a shock forms stalls and is revived, as neutrinos deposit energy into the infalling layers. That revival is the hinge. Once moving outward again, the shock climbs through shells stacked by a lifetime of fusion and meets the underside of the star's loose envelope. A first payoff arrives as the first light shock breakout, defined simply as the instant a buried shock reaches the surface, so that a sudden surge of high-energy light escapes, lasting minutes at most, and lighting the spectrum in ultraviolet and X-ray bands. But there is a catch written by the envelope. A thick inner wind and an extended atmosphere smear this flash not enough to hide it, but enough to shape its crest and tail as the new radiation diffuses and as the moving shock keeps feeding the front. What is a simple forecast? If the envelope near the star is dense, the first glow will broaden and redden sooner. If the envelope is thinner, the initial spike will be sharper and bluer before the visible rise begins. A winter visual anchor steadies the imagination. Orion above a freezing field, the red shoulder suddenly white-hot for a moment unseen by the unaided eye, while instruments catch a brief tide of a high-energy light that then softens and spreads. Next comes a climb that the human eye can follow. Visible light rises as the heated envelope expands and cools to temperatures that flood the optical bands. The second payoff is the first shape of the light curve, a fast rise over hours to a day a peak, influenced by how much energy loads the skin and by how quickly the shock encounters circumstellar material, then a settling onto a plateau or a shoulder shaped by the wind. Yet there is another catch that keeps interpretation disciplined. The geometry of the surface matters. If the star's face is uneven and the wind is lopsided, the apparent brightening will not be perfectly smooth. Small inflections will ride the climb as different sectors contribute and as the blast meets thicker or thinner lanes. The so what is a call to many eyes. Only with dense sampling across colours and from many sights can the early wiggles be distinguished from noise. And in those wiggles lies information about direction and structure that late-time observations cannot restore. A second visual anchor fixes the climb for memory, a lattice of light rising step by step across a graph, while on the sky a ruddy ember turns lemon, and then pale as it swells. The nearby belt stars unchange the outline of the hunter intact, but now anchored by a new small sun at the shoulder. Evidence from explosions in other galaxies underwrites expectations. In the first day, high energy bands fade as the shock cools, ultraviolet slides into blue, and visible light continues upward. The third payoff is an observation plan with purpose ultraviolet capable telescopes Seize the opening hour, optical telescopes step in through the first day, and radio and X-ray instruments prepare to wake as the shock begins to converse with the wind. But there is a catch tied to distance and to public perception. Betelgeuse will become dazzling yet still safe, and the sun will dominate daylight as ever. So what is careful messaging the world can step outside at dusk and dawn to witness a star reborn while daily life continues, and that calm assurance keeps attention on the science that thrives in the first nights. Now the shock meets the inner wind, and interaction brightens a secondary rise that can add colour and time to the display. Radio arrays begin to hear a new hiss as electrons are whipped to high speeds in the compressed gas, and X-ray detectors catch hard photons from hot shocked regions. The fourth payoff is a clean separation of engines. The initial rise and early colour come from the envelope. The growing radio and X-ray glow come from the wind the blast now ploughs. Track both, and the density of the inner wind and the strength of the shock can be solved together rather than guessed. A third visual anchor widens the frame a desert of space around a now brilliant shoulder, faint ripples leaving the star like rings in a dark pond, and far ahead an unseen shoreline where the bow shock waits for later months. Yet a catch awaits, even in the cleanest sequence. Dust can form quickly in the cooling wake of the shock, both in the outflowing debris and in the compressed wind. That dust can turn the light redder after the first bright climb, and can veil parts of the ejector unevenly. So what is a rotating strategy? Optical spectra and images must be paired with mid-infrared maps from instruments able to pierce new dust and to weigh it, since early dust formation records how efficiently the blast cools and how much heavy element ash the star has forged. Evidence will also appear in polarized light as scattering geometries change. Small swings of polarization reveal asymmetries in the expanding surface and in the surrounding material, adding geometry where brightness alone cannot. The fifth payoff is three-dimensional vision. With polarization angles, observers locate bright caps and dim lanes on the expanding sphere and recover the silhouette of the explosion before the remnant spreads beyond easy resolution. A fourth visual anchor returns to the human-seen rooftops and frosted trees under a night with an extra bright star, while far away a dome roof slides open and a delicate instrument turns to map the changing alignment of light waves from the gleaming shoulder. The sequence across the first days then settles into known terrain. The peak arrives its height and width, telling how large the envelope was and how thick the local wind. A plateau or a gentle decline follows as the stored heat leaks out of the expanding gas, and features on that slope hint at the structure of layers ejected and at the seams of the nearby medium. The final payoff of this section is a blueprint ready for use. By fitting the first day's multi-wavelength climb, and by tracking the onset of radio and X-ray emission, the community extracts the energy of the blast the size of the star at the moment of shock breakout, and the density and structure of the inner wind, all while the event is still young. The soft handoff points outward to coordination, because a sequence this rich only becomes a complete story if many instruments at many sites play in time. The next section therefore gathers the orchestra from small backyard cameras to the largest mirrors and dishes on Earth and in space to show how a planet can choreograph a once-in-a-lifetime observation without missing either the beauty of the sky or the secrets it offers. A planet does not watch a nearby supernova by accident. It watches by design, with many instruments moving as one. So the consequence is mastery rather than chaos, by choreographing small and large eyes across Earth and space. The community can turn fleeting minutes into a complete record that ties the core, the envelope and the wind into one readable score. To begin, the neutrino message and the first rise of light act like a starter's pistol, and the role of each facility is already written. Wide-field survey telescopes sweep Orion to lock the position and publish coordinates as plain text and rapid notices. Once the target is fixed, the largest mirrors on Earth and the instruments in orbit pivot to take spectra and images that resolve the opening changes. The first payoff is a living playbook made practical. The earliest minutes belong to ultraviolet and visible light from the shock breakout and the heating skin. The first hours add optical and near-infrared spectra for temperatures and velocities, and the first day invites radio and X-ray observatories to listen for the conversation between the blast and the wind. But there is a catch that makes rehearsal necessary. Weather maintenance and daylight can blind even the best sights, so redundancy is not waste, but wisdom. What is global coverage? A chain of longitudes and latitudes ensures that at any moment someone has dark skies and clear air, and that chain includes citizen observers whose small instruments can fill gaps in time and colour, while larger facilities slew or calibrate. A winter visual anchor fixes the sweep Orion climbs over Honolulu, then Santiago, then the Atacama Plateau, then the Canary Islands, then La Palma, then the highlands of China and Australia. A ribbon of domes opens and closes as the Earth turns, and the red shoulder stays in view somewhere at every hour. Evidence of readiness already exists in the discipline of the American Association of Variable Star Observers, a community that measures brightness with rigor and uploads results in near real time. The second payoff is cadence with depth. While flagship telescopes dissect the spectrum, thousands of precise light measurements trace the curve without gaps, catching small wiggles that reveal asymmetries and catching sudden stalls that betray dust forming in the wake. Yet there is another catch that tests coordination. The James Webb Space Telescope cannot instantly point anywhere. It follows thermal and pointing rules and needs a commanded plan. What becomes foresight target of opportunity proposals are written in advance, with triggers tied to neutrino alerts or to rapidly issued coordinates so that the telescope can pivot within its allowed window and take mid-infrared images and spectra that pierce early dust and weigh molecules in the new flow. A second visual anchor steadies that pivot a control room in Baltimore, where engineers and scientists follow a checklist, a pointing request gliding through a queue, and on a distant mirror a pattern of faint warm rings beginning to glow near the limb of a star that the unaided eye now sees as a bright point. Ground-based giants such as the Very Large Telescope and the Keck telescopes provide high-resolution spectra that turn the expanding surface into a sheet of numbers, temperatures, expansion speeds, and chemical lines that identify layers laid down in the last hours and days of the star's life. The third payoff is a physics harvest by measuring how quickly absorption lines slide to the red or to the blue, and how their shapes change. Modelers recover the density gradient of the ejector and the imprint of any asymmetry at launch. But there is a catch that makes humility a partner. Instruments saturate when the target is bright, and the supernova will be bright. The what is adaptation by exposure control and neutral density filters, by short integrations stacked in rapid bursts, and by a division of labour in which small telescopes less easily blinded contribute crucial early measures that keep the curve continuous while the giant mirrors adjust. Next comes the radio and X-ray embrace, because interaction with the inner wind writes in wavelengths that are not seen by human eyes. The Atacama Large Millimeter Array maps the fresh shock as it plows through molecular gas close to the star, while the Jansky Very Large Array and other radio networks catch the first synchrotron hiss from electrons accelerated at the shock front. The fourth payoff is a clean cross-check. When radio brightness rises and X-rays flicker the density of the wind, and the efficiency of particle acceleration can be solved together with the optical curve, making the early light not just beautiful, but diagnostic. Yet another catch lies in the crush of data. Thousands of spectra, millions of photometric points and radio measurements at many frequencies will arrive within days. What is a shared backbone data standards. Common timestamps and open portals allow rapid modelling that can be updated hourly, and summaries can circulate in plain language so that both professionals and the public see a coherent picture rather than a blizzard of fragments. A third visual anchor brings the human scale back into frame. A small backyard telescope tracks the star from a snowy garden. A teenager clicks upload on a calibrated measurement, and halfway around the world a scientist folds that point into a fit that confirms a tiny shoulder. In the rise, a shoulder that marks the blast encountering a denser lane in the wind. Coordination also includes education because the brightest nearby supernova in living memory will draw eyes who do not read journals. The fifth payoff is stability under wonder observatories. Post updates that repeat the safety context in clear terms, explain what is expected next, and invite participation in simple tasks that add to the record, keeping anxiety low and engagement high. But there is a catch written in human attention. Rumour travels faster than correction if silence leaves a gap. What is to speak early, often and plainly with a single shared message about safety and about the beauty of the unfolding science. The sequence then widens into longer timescales. After the first week, schedules shift from frantic minute-by-minute capture to a measured campaign of nightly imaging, weekly spectra and periodic radio, and infrared mapping all tuned to track the plateau, the decline and the first signs of dust forming in the ejecta. The final payoff of this section is a durable blueprint that turns astonishment into knowledge by assigning each instrument a window where it delivers unique information, and by weaving those windows into an unbroken cloth, a once-in-a-lifetime sky event becomes a data set for generations, a map of how a single red star ends written across every colour we can see. The soft handoff points beyond the peak into the years that follow, when the bright day fades and the debris begins to speak in echoes and in expanding filaments, and when the sky remembers the blast by carving a new shell where a quiet star once breathed. After the blaze, the sky does not return to silence. It learns a new language spoken in expanding debris, cooling ash, and scattered reflections that keep the story alive for years, so the consequence is continuity without fear. Earth remains safe while the space around Betelgeuse turns into a visible laboratory where matter is recycled and time is measured in rings. The first payoff arrives with echoes a simple idea with exquisite geometry. Light from the first days races outward, strikes sheets and filaments of dust around the star, and scatters toward Earth along longer paths, so the sky brightens again in faint, thin arcs that appear to grow across the darkness even though nothing physical moves that fast. But there is a catch that enriches rather than confuses. These echoes trace three-dimensional structure because each arc marks a surface of equal travel time, a rippling paraboloid in space that slices the circumstellar medium at a known delay. So what is a ruler by measuring the changing radius and brightness of these arcs, and by comparing colours, observers recover distances to dust layers, grain sizes and orientations of sheets that were only ghosts before the flash. A winter visual anchor fixes the image, a lattice of pale rings expanding over weeks against Orion's shoulder, as if frost were blooming on dark glass, each ring the delayed memory of that first brilliant minute. Evidence grows as instruments specialize. The Hubble Space Telescope takes crisp optical images that freeze the thin echoes against background stars. The James Webb Space Telescope measures mid-infrared glow, where dust warmed by the pulse re-emits gently. Ground-based wide-field cameras keep nightly watch so that no arc is missed when it sweeps across a dense star field. The second payoff is chronology. Echoes near the star appear first, followed by arcs that map the bow shock months or years later. And finally, if detached shells lie along the star's path, those shells light in sequence like distant lanterns, turning decades into a readable timeline of the neighborhood. Yet there is a catch that keeps attention on calibration. Echo brightness depends on grain composition, and size and color terms must be stable to keep fits honest. The so what becomes method, multi-wavelength observations must share timestamps and filters so that modelers can separate geometry from grain physics without mixing the two. A second visual anchor widens the frame, a desert of space, where a thin copper crescent marks the bow shock now traced by echoing light that glides along it like a wave touching a shore. The narrative then turns to debris, the expanding material forged in the star's deepest layers that now cools and builds new solids. Evidence appears in spectra that shift from hot broad lines to cooler narrower features as the ejecta expand and thin, and in mid-infrared signatures that reveal molecules forming in the wake. The third payoff is renewal. Carbon and oxygen lock into carbon monoxide. Silicon and oxygen lock into silicon monoxide. Refractory grains condense first as tiny seeds, and then as larger particles that may survive to enrich the interstellar medium. But there is a catch. Shock heating and radioactive decay can both keep the gas too warm for grains to grow, or can shatter small grains as they try to form. What is a contest the observations can score when the Atacama Large Millimeter Array maps molecular lines, and the James Webb Space Telescope traces warm dust growth winds. When those signatures lag, and optical light stays less reddened than expected, destruction leads. A third visual anchor settles the imagination within the fading sphere. Clumps glow like embers in ash, some coalescing, some crumbling, a slow weather of powder in a cavern of light. The expanding debris also sculpts the newborn remnant. Filaments and knots move outward at thousands of kilometers per second, but the remnant's visible shape depends on where the blast meets dense wind. The fourth payoff is a motion picture in plane units. By measuring the expansion in arc seconds per year and tying it to distances known from earlier work, observers turn shimmering into speed and convert outward motion into kinetic energy, checking models that estimated the force of the explosion from the first week's light alone. Yet another catch remains, and it is the seed of future beauty. As the blast enters the bow shock, and then the patchwork beyond reflected light returns again and again, while fresh shock fronts brighten in radio and X-ray. So what is patience as a virtue? The event that seemed a single night's marvel becomes a program of steady watching that continues to teach through seasons, and each new rise on the long tail is a probe at a new radius. Safety context threads through these years without strain. The distance remains large, the energies dispersed, and even when the remnant shines in radio and X-ray, the flux at Earth is small compared to everyday natural backgrounds. A fourth visual anchor keeps the tone grounded, a backyard under autumn leaves. Orion, the same familiar figure, the shoulder, now a resolved shell in large instruments, but still a bright point to the eye, a reminder that wonder and ordinary life coexist easily. The narrative folds echoes and debris into chemical consequence. Dust born in the cooling ejecta and dust preserved in the pre-existing wind both face survival tests when the forward and reverse shocks strengthen. Some grains are crushed or sputtered, others escape into the local arm as hardy seeds for future clouds. The fifth payoff is cosmic recycling, measured, not merely imagined, by tallying dust masses over years, and by comparing composition before and after shocks, the community learns how massive stars enrich their surroundings, a key to how later generations of stars and planets gain the heavy elements and solids they need. But there is a catch set by clumping. Dense knots can shadow dust behind them, and may shelter molecules that would otherwise break apart, making the remnant's chemistry patchy, and its growth of solids uneven. These sow what is high resolution as a requirement only arrays that can resolve fine structure in the millimeter and submillimeter bands paired with sharp optical and infrared images can weigh these pockets accurately instead of averaging them away. The sequence of the years then clarifies. The day-bright shoulder becomes a bright point with a soft halo, then a ring with scalloped edges, then an expanding tangle, and finally a young remnant whose size can be drawn on maps, and whose light echoes still glide along distant sheets. The final payoff of this section is a promise that matches the stakes set at the beginning. The aftermath enriches the galaxy, but does not endanger Earth, and the sustained campaign to measure Echo's molecules' dust and motion turns a passing spectacle into a generational data set. The soft handoff looks outward to comparison, because the meaning of Betelgeuse's story becomes sharper when set beside other red supergiants before and after their ends, and when patterns and outliers both are used to refine the models that will read the next giant's signs without confusion. Lessons draw their power from comparison, and Betelgeuse becomes clearer when set beside other red supergiants that breathe, shed, and end under slightly different rules, so the consequence is refinement. By mapping patterns and outliers across many giants, the community turns a single star's restlessness into a forecast with narrower bounds and fewer illusions. The first payoff arises from a gallery of faces. Interferometers have imaged the mottled discs of Antares Muchepe and Cei Tauri, each showing continent-sized convective cells and slow sways that echo Betelgeuse's surface weather. But there is a catch that guides restraint. The sizes and lifetimes of these cells vary with luminosity, temperature, and mass, so a deep fade in one star may align with convective geography that another star cannot sustain. So what is a calibrated expectation? Surface storms are a class behavior, yet their strength scales with the envelope, which means Betelgeuse's most dramatic curtains are unlikely on a lower luminosity cousin, and could be modest beside the upheavals on a more extreme neighbour like Canis Majoris. A winter visual anchor fixes the contrast a row of slow, turning embers, some softly speckled, one veined with broad dark rivers, their edges feathered by heat spilling into space. Evidence expands when winds and shells are compared. The Atacama Large Millimeter Array has mapped Canis Majoris with colossal plumes and arcs that mark a violent, uneven outflow, while Betelgeuse shows gentler lanes and a clean bow shock with modest corrugations. The second payoff is a lever on hazard and display. Stronger pre-existing mass loss in the final years can turn a future supernova into a bright interacting show that lingers while a quieter wind yields a sharper, briefer rise. Yet there is another catch. The stars most prone to extreme mass loss sometimes shed enough envelope to change class before death, shifting blueward and confusing the tidy expectation that all red supergiants will end as red. What is a branching path? Betelgeuse's present temperature and wind argue for a red supergiant ending, but the gallery of peers warns that nature sometimes edits late. A second visual anchor steadies the mind a desert of space, where three paths diverge, one marked by thick, dusty lanes, one by a smooth, faint fog, one by a wind that thins and a colour that shifts to orange, then to yellow. Progenitors of known nearby core collapse supernovae supply the next comparison. Several plateau-like explosions in other galaxies have been linked to red supergiant progenitors with masses around 10 to 17 times that of the Sun, a mass range that matches Betelgeuse's probable scale. The third payoff is a tightened prior. The light curves and early spectra of those events show signatures that can be directly mapped onto predictions for Betelgeuse, including a fast ultraviolet surge, a bright visible plateau shaped by a large cool envelope, and radio and X-ray rises governed by interaction with a moderate wind. But there is a catch called the missing high-mass red supergiant problem, a short phrase that names a real puzzle. Direct images of progenitors rarely show stars heavier than about 18 solar masses, making the common plateau-like explosions raising questions about whether the most massive red supergiants quietly collapse to black holes or explode in ways that hide their origins. The so what is humility with purpose. If Betelgeuse sits near the upper end of the comfortable range, it becomes a crucial test of whether a heavy red supergiant can still deliver a classic display, or whether late mass loss and structure steer it onto another branch. A third visual anchor frames the stakes a wall of ancestor portraits in a quiet gallery, each a faint smudge on a pre-explosion image labelled with a mass and a fate, with a blank labelled Betelgeuse waiting for a final date and a final class. The narrative turns to fine signs that precede some endings. Flash spectroscopy defined as spectra, taken in the very first hours that show narrow lines, from circumstellar gas suddenly ionized by the first light, has revealed that several recent supernova were wrapped in dense shells laid down only years before collapse. The fourth payoff is a realistic watcher's checklist. If Betelgeuse begins a sustained upturn in mass loss, seen as stronger molecular lines and new inner arcs, and if the next deep dimming arrives paired with that rise rather than with a simple surface rhythm, then the case strengthens for a late dense cocoon that could produce flash features and a longer, brighter early light curve. But there is a catch that rejects overreach. Some red supergiants show no such late surge and still explode without warning. Beyond the neutrino shout, so absence of a precursor does not mean absence of an imminent end. What is to maintain two plans at once? One tuned to a quiet envelope and a sharp dawn, one tuned to a thickened wind and a dawn that becomes a drawn-out morning. Comparison also refines interior inference. Period drifts measured across Mu-Cephei and other giants correlate with changes in mean radius and mass loss, and those correlations make it possible to read Betelgeuse's pulsation history not as a random walk, but as a structural diary. The fifth payoff is a bridge from skin to core if Betelgeuse's principal period lengthens steadily, while the average brightness cools slightly and mass loss rises. Models that fit. Peer stars say the envelope has relaxed outward, and that neutrino cooling is biting harder within shortening remaining stages without putting the end at the door. Yet another catch demands sobriety. Magnetic fields on these giants are weak and tangled, but their influence on mass loss geometry can be larger than their raw strength suggests, and different stars host different field patterns. What is a caution against copying too literally patterns seen on Antares may rhyme with Betelgeuse, but need not match meter for meter. A fourth visual anchor returns to the winter sky, Orion on one side, Scorpius on the other, in a summer memory two bright red hearts that share a kind but not identical weather. The narrative knits agencies and instruments into these lessons. The Gaia mission's improved distances recalibrate luminosities and therefore progenitor masses. The Very Large Telescope and the Keck telescopes resolve surfaces and lines. The James Webb Space Telescope and the Atacama Large Millimeter Array chart dust and molecules. The American Association of Variable Star Observers supplies dense light curves that reveal beats and drifts the giants share. The consequence is a mature framework into which Betelgeuse fits as a well-observed citizen rather than a solitary wonder. The final payoff of this section is practical confidence. By knowing how other red supergiants breathe, shed, and sometimes signal their last years, the community can set crisp thresholds for concern and can craft messages to the public that promise spectacle without harm. The soft handoff returns to the human edge of the story. The sky will do as it will, but watchers can choose their posture. In the last section, the narrative turns to waiting without fear, to steady monitoring, clear language, and seasonal awe that keeps curiosity high, while the star takes the time it needs to write the last pages of its long book. Waiting becomes a discipline rather than a pause when the sky holds a promise that may bloom in a season or in a century, so the consequence is agency. Without anxiety, the community can watch Betelgeuse with care, speak plainly about safety, and let wonder rise on schedule while every real signal will be caught in time. To begin, readiness replaces prediction. Observers write plans that assume the star may wait, and those plans still deliver value every clear night. The first payoff arrives as a structure anyone can follow. The Neutrino Alert Network continues to listen for the only decisive early messenger from the core. Wide field patrols in visible light keep cadence on the red shoulder. Infrared instruments check for fresh dust. Radio arrays sample the inner wind, and volunteer observers maintain a continuous curve that makes any new deviation obvious within hours. But there is a catch that turns patience into work. Data without context can spark needless alarms when weather instrument drift or seasonal gaps create false steps in a light curve. The so what is a simple rule shared widely. Any claim of a new plunge or surge must appear in multiple bands from multiple sites with calibration checks posted alongside. A winter visual anchor steadies this rhythm. Orion rising over a frozen field, a small backyard telescope glinting with rime, a notebook page with neat columns of time and brightness, and far away, a quiet control room where a steady trace from a neutrino detector crawls across a screen without fuss. The narrative keeps the stakes clear and calm. Betelgeuse sits far enough away that even its most glorious ending means spectacle, not harm. The second payoff is trust built by repetition. Public updates open with distance, with plain safety lines, with the expected order of signs if a true countdown begins, and with what to look for in the sky on any given week, whether nothing unusual is happening or not. Yet there is a catch written in attention itself. When nothing dramatic occurs, interest can ebb. When a small change occurs, rumour can rush in to fill the vacuum. The so what is to make the ordinary interesting. Seasonal features become chapters. The star's slow rise in early evening as winter deepens its colour compared to Rigel's cold blue, the tilt of the belt over rooftops, the way thin clouds sharpen or soften the hue. A second visual anchor paints that continuity, a line of bright windows, breath rising in the cold, Orion angled above Betelgeuse, steady and warm, a familiar ember that marks time for families and for instruments alike. Evidence of steady progress continues even without drama. Distances tighten with improved astrometry. Angular sizes refine with new interferometric baselines. Dust maps sharpen with better calibrations, and period fits gain power as the archive lengthens. The third payoff is forward motion, measured in clarity, not in crisis. Each season cleans a lens through which the future event will be read, so that when the first decisive sign arrives, the interpretation will be swift and strong. But there is a catch that protects against complacency. Instruments age, funding shifts, and expertise must be renewed. The so what is to braid training into the watch. Universities and clubs host nights where novices learn to measure and calibrate. Observatories rehearse alert responses as fire brigades do. Software pipelines are tested with simulated signals so that no one meets the first minutes unprepared. A third visual anchor follows a thread from classroom to sky, a circle of students around a laptop, a practice alert on the screen, a small telescope slewing to a test field, and in the corner of the frame the real Orion rising a promise rather than a demand. Communication stands as its own craft. The narrative voice that carries the story to the public avoids jargon sketches, images before statistics, and places every fact beside a simple comparison. The fourth payoff is resilience. When a rumour misstates a brightness change or a calendar date, a prepared message already exists that gently explains the margins of measurement and invites the curious to check live plots rather than share unverified claims. Yet another catch must be held openly. Uncertainty is not ignorance, it is the shape of what is not yet known. What is to say that out loud? A star can live for years in late stages without visible drama. A spectrum can hint without proving. A period can drift without committing to an end. Naming these truths protects trust when forecasts remain broad. A fourth visual anchor returns to the shared sky, a town field under a winter festival, warm cups in cold hands, Orion shining above booths and laughter, the red shoulder a steady companion science and celebration, unharmed by the absence of breaking news. The narrative folds in ethics and access. A nearby supernova will belong to everyone who can step outside. The fifth payoff is inclusion by design. Data portals remain open, summaries appear in multiple languages, and simple observing guides show how to watch with eyes alone or with small instruments. Schools adopt the star as a seasonal project, plotting brightness against date-drawing Orion on maps, learning the difference between a flare from a phone camera and a true change in the sky. But there is a catch that asks care. When the neutrino network finally speaks, hours will be precious. Planning must prevent crowded roads to mountaintops and unsafe gatherings. What is distributed wonder. Cities dim public lights for an hour at dawn or dusk. Museums host early openings. Radio stations describe how to look, and the observation load spreads across backyards and sidewalks, as well as observatories. A final visual anchor closes the circle, a neighbourhood street at pre-dawn, Orion large and low, Betelgeuse bright, a few neighbours in coats pointing quietly, while a robin calls once from a hedge. The section ends where it began, in discipline that leaves room for joy. The watch continues because the stakes are knowledge and shared experience, not emergency. The final payoff of this section is a composite picture ready to be acted upon. If the neutrino burst arrives, instruments will turn. If it does not, the archive will deepen and sharpen, refining every model of how giants live and end. The soft handoff leans into rest. The next and closing passage will lower the voice and let the mind drift, holding Orion and its red shoulder in a calm frame where a familiar ember steadies winter nights, while the long story of a massive star continues at its chosen pace, promising a spectacle to be met with readiness, with wonder, and with sleep well earned. Night settles into a gentle stillness, and Orion hangs with easy poise over rooftops and fields, the red shoulder of Betelgeuse a calm ember set in a pattern older than stories. The consequence of this long journey is not urgency, but release. Knowledge is gathered into soft certainty, where it matters most. The star is distant enough to promise spectacle without harm, close enough to promise detail that will enrich understanding for generations, and steady enough now to offer a season of quiet watching that feels like a ritual rather than a vigil. A winter horizon offers a simple image to hold frost silvering a fence, a thin hush in bare branches, a slow turning sphere far away, breathing in light that has crossed years to arrive with no demand. The mind drifts across the steps already marked. Surface weather has been named and weighed a language of bright plateaus, and darker basins moving like continents of heat. Pulsation has been timed into patient tides whose faces can be penciled on a calendar. Dust, the star's favourite disguise, has been folded into memory as a curtain that sometimes falls and sometimes lifts, never a threat, always a lesson about how grains condense and drift. Around the star, a faint architecture of shells and lanes now reads like a musical score. The blast will one day play, while far ahead a curved shoreline of a bowshock waits to turn the first echoes into thin rings that will teach distances in light and time. Deep within the furnace keep steps that are known by class, even if unknown in date. A quiet bead hardens and brightens far below the surface, a core moving through last fuels toward a final release written by gravity and heat and neutrinos, a script that will open not with light, but with a whisper of particles that race through stone and water and announce the first seconds before any gleam. That early whisper is already accounted for by instruments sleeping lightly beneath mountains and ice. Plans rest in drawers and in servers. Sequences are rehearsed by hands at backyard instruments and by teams guiding the largest mirrors in deserts and on volcanic heights. When the first hint arrives, the world of watchers will turn not with panic but with choreography, a modest and elegant pivot that respects both the sky and the ground. Until then, the lesson that matters is gentler. Waiting can be its own craft. A neighbourhood can make a habit of stepping outside on clear evenings, measuring distance with breath in the cold, comparing the red shoulder to the blue foot of the figure, noticing how thin cloud brightens or softens the hue, and letting curiosity move at the speed of seasons. Schools can pin simple charts by classroom windows and add one small dot of brightness, each clear morning a slow graph that teaches patience and care. Clubs can host nights where a handful of learners learn to set exposure, to check calibration, to write down the time, and to upload a clean point that joins thousands of others in a river of careful light. Museums can keep a map of Orion at the door and replace the page each month as the figure tilts and the horizon changes so that visitors see sky as calendar and not as noise. None of this requires alarm. Uncertainty is not a cliff, but a meadow, and walking through it is restful when the path is clear and the destination is not rushed. The world will someday wake to a neutrino shout carried by quiet wires, and then the sky will offer a dawn within night as a red star becomes a brief small sun. That day will be just another day, the sun rising. As always, the morning commute moving as always, and yet a new light will rest on familiar eaves at dusk and on quiet snow at dawn, and in that interval the universe will open a door wide enough to walk through without strain, for now the ember glows. Winds stir over continents of heat on a face no eye can see directly, and a loose envelope exhales into a cloak of dust and molecules that the mind can imagine as breath on glass. The hunter's outline remains clean belt aligned over chimneys soared, faint and misty, the red shoulder steady as a heartbeat in a sleeping house. The story has reached a place where learning and rest can share the same chair. Instruments keep their cadence without drama. Software sleeps with a watch set, and the open sky remains the most generous teacher there is. The mind can set down the ruler and the clock, and let images float a desert of space, with a thin copper arc like a shoreline, a slow-turning sphere patched with moving light, a lattice of rings spreading across dust sheets like frost patterns blooming on dark glass and far below ground. A quiet hall of clear liquid waiting for a ripple of neutrinos that will come one day and change the routine of a single night. Until then, the star is not a worry but a companion. It holds a promise at a scale that is human to receive a sight, to remember a set of measurements, to carry forward a shared breath of awe that links neighbourhoods and mountain domes and ships at sea. Calm returns to the room, to the street, to the field, and to the sky. The ember on the shoulder of the hunter steadies winter and early spring. Wonder keeps its own time, and sleep comes more easily when the night has a familiar anchor. The story will continue with or without the page being turned tonight. It is enough to know the page is written and waiting. It is enough to watch the ember and let the eyes close, Orion framed at the window, the world safe, the future bright, and the long book of a massive star unfolding at its chosen pace.